Good morning. My name is Kelly Merlot. This is Nathan Morgado, Edward Delatois, and Michael Soretti, and today we'll be presenting our senior design project titled the Red Line Track Vibration Analysis. Our client for this project is the MBTA. They are a division of MassDOT that provides transportation for Eastern Massachusetts. Their most popular mode of transportation is their subway, but they also provide transportation via buses, ferries, and other trains like the commuter rail. Each weekday, they provide transportation for roughly 1 million customers, and more specifically, the MBTA Red Line provides transportation for over 250,000 customers. This is a large portion of the population that can be affected by potential projects like ours. Has anybody here actually ever ridden the MBTA Red Line and had a smooth, comfortable ride? Smooth, comfortable ride are key words there, okay. So for those of you who haven't ridden the Red Line, the reason that I highlight those words is because the MBTA Red Line is bumpy all the way from Braintree to Outway, which leads us into our project problem statement discussed by Nathan.
So the problem that the MBTA has been having has to deal with the tracks that the Red Line trains are riding on. Here in the picture can be shown a breakdown of the track and the base layers that make it up. And an important part of this project has to deal with the track ballast, which is the large stones that the rail sits on. And due to inclement weather and constant usage, the track ballast can shift and develop low spots. And these low spots can cause the train to experience high amounts of G-forces when ridden over, which is not ideal. And this project is servicing now, as the MBTA will be implementing a new fleet of Red Line cars later this year, and they want to make sure that they're not going to be damaged prematurely. So for our project requirements, we had some main priorities and some secondary priorities. For our top priorities, we wanted to create a sensor for this specific application that would be able to read the G-forces. Next, we wanted to create a housing unit and determine where and how we were going to attach it to the train. After this was done, we can move on to the secondary priorities. And of these, we were going to be able to implement it later this week or next week, and we can get it to the MBTA, and they're going to actually do the data analysis and collection for us. Unfortunately, we're not going to be able to add the GPS tracking to it, as it was too much electrical knowledge for us, and we didn't have time. So for our project constraints, the sensor had to be able to read a maximum of plus or minus 50 G-forces, which was required by the client. Since the sensor would need to be on and transmitting data for the entirety of the ride, it would have to last for at least 6 hours to capture all the required data. Here in the picture can be seen the axle box we wanted to mount the sensor and the maximum dimensions of the area that we had for the housing unit. And lastly, the MBTA wanted the sensor to be able to communicate wirelessly through Bluetooth to an operator on the train with a Bluetooth compatible device, and they could read the data. So for our design options, we considered 3 different options for this project. The first was a completely commercial design, which would cost around $200 to $250. And this one was ready to use when bought right off the shelf. Unfortunately, it did not have the wireless connectivity they were looking for, and the maximum dimensions were a little bit too large to fit on that axle box location. Second, we looked at a shelf to assembly option, which would require a little bit more time due to the programming, and it had the highest cost around $400 to $500. And unfortunately, this one also did not have the wireless connectivity they were looking for. Lastly, we looked at a completely custom option, which satisfied all the requirements from the MBTA, including that wireless connectivity, and it actually ended up being the cheapest option, around $100 to build the entire sensor. Even though this one was the idea that would take the longest amount of time to implement, it was one that was chosen by us and our client to be the best option. Here's the final design for our sensor. It can handle a range of G-forces of plus or minus 200 Gs, and that's due to not being able to find a sensor of lower caliber that was compatible with our Arduino Nano microcontroller, which runs our unit. It has a battery life of 13 hours, so it can capture all the data needed. Here is our SolidWorks design. So it can be seen that the dimensions are small enough to fit in that axle box location. And also it has the Bluetooth connectivity that the MBTA was looking for. Next, Mike will talk about the design for the housing unit.
Alright, for our sensor design, we had to create a protective housing unit that was based off of the sensor's dimensions. The housing unit needed to be able to open and close for easy access to the sensor's components, and initially we used a latching design for accessibility. Then, since Bluetooth has trouble communicating through various materials, we designed the box so that the Bluetooth component was exposed, but there was no interference with communications. To attach the housing unit to the steel frame of the train, we screwed in a rare earth magnet into the bottom of the design. Then we also had to keep in mind that the design had to be as compact as possible to fit anywhere along the steel frame of the train. And with that compact size, we needed to keep in mind that the sensor needed to fit in the housing unit as rigid as possible for accurate results. To reduce the size of the housing unit and to make it more compact and rigid, we placed the magnet within the housing unit. We removed any excess space and we switched to a lid that securely fit and could be popped off using a tab. The housing unit was printed in-house, 3D printed in-house using PLA, which is a very affordable material. And even though it's not soluble in water, it will degrade if exposed to water. But our sensor will be used in ideal weather conditions, so that won't be a problem. Also, PLA will degrade if exposed to high heat, but it won't be placed in any areas of heat on the train, so that also won't be a problem. Here's our sensor design with all the components exposed. And to the right, you can see it fits very rigidly within our box design. You can see the Arduino Nano, which is the microcontroller. We wrote a program for it to communicate wirelessly through our Bluetooth component. We also have the 3-axis accelerometer, which is going to collect the shock variation data off the red line. Then we have the battery connection, along with a switch assembly and an indication light for the power. And then we have resistors, a capacitor, and a perf board to integrate the electrical circuit. We conducted 3 types of testing to make sure our sensor was calibrated and collecting accurate results. We had a stationary transmission test, we had a distance transmission test, and we had a dynamic transmission test, which Kelly will expand on these 3 tests further.
As Mike said, the first test that we performed was a stationary transmission test. This was to see how well our sensor would compare to a calibrated sensor at rest. A calibrated sensor at rest has 3 axes. 2 that bounce around 0, which corresponds to acceleration or lack thereof acceleration in the front, back, and left and right directions. The final one bounces around 1 g-force, which corresponds to acceleration in the vertical direction. As you can see, our sensor data on the left has a similar profile. We have the 2 axes that bounce around 0. However, the final axis that corresponds to the acceleration in the vertical direction only reads about 0.75. This, however, is numerically not 100% accurate, but for our testing profile, we considered this to be successful. The second test that we performed was a transmission distance test. This was to see how well our Bluetooth would do in a variety of environments and at a variety of distances. The 3 environments that we tested in were an open area, closed area, and a moving area. The open area was done in a field where the transmission signal could move freely. The closed area was done inside a building where there would be obstacles where the transmission signal would have to go through, and the moving area was done inside a vehicle. As you can see, the open area was able to get to a distance of 12 meters. This was then reduced to 10 meters in the closed area. And due to vehicle limitations, we were only able to test up to 3 meters. However, we expect that this testing would be successful at further distances. In the end, we recommend using our sensor at less than 10 meters, and that's because at further distances, the Bluetooth can actually drain power, and that's not what we're looking to do with our sensor. The final test we did was the dynamic transmission test, and this was to try to replicate the sensor on the red line as close as possible. To do this, we took our sensor as well as a calibrated sensor and placed them in a car and took them around a stretch of road. During this test, both sensors were able to pick up disturbances in the road that caused high g-forces, such as potholes and uneven road. An example of this can be seen on these 2 graphs, our sensor on the left and the calibrated one on the right. You can see that they have a similar profile picking up a high g-force disturbance. However, numerically, the calibrated sensor read around 3.2 and ours only read around 2. But again, we're not looking for specific numerical data, so the profile matching was what we were considering a success. And now Eddie will talk about project planning.
Okay, so moving on to the timeline of the project. As you can tell, this project is mostly computer and electrical based. Us being 4 mechanicals, we definitely had a tough time getting off the ground. However, it was about the start of this semester. We had a prototype built, both the electrical circuit and the physical housing. And again, us being mechanicals, once we were able to hold something physical, we really got to see the light at the end of the tunnel. We started putting in a ton of hours, coming in early and staying late, because we wanted to make sure that we saw this project through to the end and met our deadline. As Nate had mentioned earlier, the last step of this project is the sensor implementation. So we're going to be sending the sensor up to the MBTA sometime either this week or next. We're going to get some real-time data and see just how successful our project will be. Looking now down at the bottom of the screen here, you can see the contributions. So these roles that we have are not really explicitly delegated to us, but rather we fell into these roles quite naturally. So for myself, after high school, I went to a vocational high school. I was employed as a motorcycle mechanic and then at an automotive dealership as a technician. So working with my hands is what is most comfortable to me and what felt most natural to me. So handling things such as soldering and creating physical design is what I gravitated towards. Next, Kelly, along with being the team lead and delegating some of the work to us, she currently holds an internship at a manufacturing company where they produce capacitors. So she has good fundamental electrical knowledge, and also she was able to ask for help and guidance with professional electrical engineers anytime we needed it. Next, Nathan last summer held an internship where he handled materials research. He did a lot of work with material safety data sheets, logistics such as purchasing, planning, and implementation materials, so he was a perfect fit for that role. And finally, Mike currently holds an internship as a design engineer intern. The company works with design seals for a bunch of aerospace companies. He has a lot of good access to prototyping materials and softwares, and he's surrounded by a lot of creative minds. So anytime we needed help, we were able to reach out to them. So now moving on to the budget. We had an initial budget of $5,000, so we had a lot of room to work with this project. However, as Nate mentioned, other than building the sensor, the second focal point of this project was keeping costs to a minimum, as it is with most projects. So for prototyping, we spent about 5% of our budget, which is $300, and we have a remaining budget right now of $4,600. The reason we were able to keep this so cheap is if you look at the cost breakdown below on the screen, the other sensors that we were considering were pre-built, manufactured, and the price of those sensors is associated with overhead that the company face, such as labor, scrap, hazardous waste removal, meeting profit margins, so on and so forth. Us being a bunch of college students working with the MBTA, we didn't have to meet any of those, so we were able to keep costs to a minimum. For project challenges, we had a lot of them. So first off, as I've iterated multiple times, it being an electrical project, it was tough for us. However, when one door closes, another tends to open. So we took a positive out of this. We got to expand our knowledge about this project. We learned a ton of new skills, and we also got to communicate with a community of people that we might not usually be in touch with throughout the program here as mechanicals. Next, we were given very specific constraints and measurements from the MBTA. They were very strict on physical dimensions and electrical dimensions as well. We had to go through a ton of component changes, multiple iterations of the housing itself. It was definitely tough for us. However, as I said, we were able to build and get it working. And finally, we had difficulty scheduling. We all hold different internships currently, so we have different schedules. Some of us are in more or less classes. The classes are at different times of the day. We're pretty geographically dispersed as a team. And also, we have social lives that we do try to maintain to the best of our abilities. So for the project outcome, we can consider this project a success because the MBTA now has a working sensor that can characterize vibrational data. And we also met the second focal point of the project, which was keeping costs at a minimum. Also, because we built this sensor custom, replication is going to be easy. The MBTA has a 3D printer and the same materials. So if they see fit, they were able to print this and build it themselves, and they can put it on different parts of the train, or they can put it onto different trains themselves. Also, because it's custom, it's very easily manipulated. It's more future-proof, I guess you could say. So they can modify it any way they see fit. They could add GPS coordinates to the G-force spikes. They could add additional data loggers, so on and so forth. So hopefully, with the implementation of this sensor, we're going to be able to provide a smoother ride to the customers with the MBTA for years to come. Are there any questions?